Thanks very much for that introduction, and thanks for the invitation to give this lecture. It's always good to see lots of bright, young, shiny faces, and I look forward to hearing some of your questions at the end of my talk. So, my title is taken from a painting by Gauguin, which I'll come back to in just a moment. These, I think, are very basic metaphysical or philosophical questions about human beings and their place in the universe. But as you already heard from Rajesh, I'm going to address these from the point of view of physics, more specifically of particle physics and its connection with cosmology. So this is an image representing our current understanding of the universe. So here we have a typical satellite, which looks back at stars and galaxies towards the beginning of the universe that we call the Big Bang. Now, that Big Bang, according to the current estimates, took place 13.8 billion years ago. And since then, the universe has been expanding, and currently the size of the universe that we can actually see is something like 10 to the 28 centimeters across. So this understanding of the universe, of course, opens or reopens many fundamental questions. One is, what is the universe made of? The matter that is in the universe today, which is not just the visible matter, but also, as I'll discuss in more detail, an enormous amount of invisible dark matter. What is that matter made of? Then obviously there's a question of what has been going on since the Big Bang. What happened back towards the early universe? Now, if we look back, the earliest thing that we've been able to detect so far is radiation that was emitted about 380,000 years after the Big Bang. So if you like, the birth cries of the universe that were emitted when atoms were formed. Prior to that, there were no atoms. So we'll be talking a little bit about what happened then. And of course, the third of those questions is what is going to happen in the future? Will the universe continue to expand forever? Or will its expansion stop, and will it reverse itself in some sort of big crunch? And that's another one of the issues that we're going to discuss in the course of this lecture. So as I said, these basic physical or metaphysical questions are taken from this famous painting by Gauguin. So here we have a bunch of people on some South Sea island who are putting these very basic questions. The point of my lecture is to argue that what we do in particle physics, what we do in cosmology, what we do in experiments at CERN, and specifically at the Large Hadron Collider that we operate at CERN, our objective is to try to at least address these questions. We can't promise to give all the answers, but at least we're going to try. And as we'll hear later on, at least some of the answers maybe have already been indicated by experiments at CERN, at the Large Hadron Collider. Okay, so let's dig down a little bit deeper into our understanding of the universe today. So what I've got here is a ruler on a logarithmic scale, going all the way from 10 to the plus 28 centimeters over here. As I said, that's the size of the visible universe today. 10 to the 28 is a very, very big number. So I have a way of thinking about it. You think of the American budget deficit, you express it in cents, and you square it, and you get something like 10 to the 28. Before Trump. After Trump, maybe another couple of zeros. Well, at least one zero. Okay, so that is the very largest scale that astronomers think about. And then at the other end of the ruler, we've got the very smallest scale that physicists speculate about. That's the scale of 10 to the minus 33 centimeters, 10 to the minus 32 centimeters, where our understanding of space and time break down because gravity itself becomes a quantum phenomenon. And there's some experts in the front row who are working on that, and if you want to know what happened then, go ask them, okay? So about halfway along this logarithmic scale, we've got the human scale. So here we have Albert Einstein and his kid sister when they're about 1 meter tall, as I said, roughly speaking, halfway along this logarithmic scale. So of course there's a lot of other scales here. There's galaxies, the distance between the Earth and the Sun, the radius of the Earth. And then inside Albert Einstein and his kid sister, I've marked scales like the size of an atom or the size of a proton. So physicists over the last century or so have got to understand quite a lot about what goes on inside Albert Einstein and his kid sister. So we know that they were made of molecules. Those molecules contain atoms. Those atoms have nuclei in the middle with clouds of electrons around them. And those nuclei are made up out of particles that we call protons and neutrons. And then at the most fundamental level of nuclear matter, those protons and neutrons are made of things that we call quarks. Okay, so that's what we understand so far. And as we'll be discussing later on, of course, we're seeking further understanding, going further back with our accelerators to smaller and smaller distances, earlier and earlier times, closer to the Big Bang. Now, the astronomers tell us not only how big the visible universe is today, but they also tell us about how the density of matter and energy is made up. What they tell us is that in addition to the visible stars, there is also a lot of invisible dark matter. And one of the biggest puzzles that cosmologists have is what is that dark matter? And one of the things that we particle physicists hope to bring to the table is a discovery of what that might be. Maybe it's made of some particles that we can make in our accelerators. So the LHC is our largest accelerator at the moment. You can think of it as being a super microscope looking deep down inside Albert Einstein and his kid sister. It's also, in some sense, a super telescope that may be able to answer some of the questions, such as, for example, the nature of dark matter, which are posed by the astronomers and cosmologists. Okay, so let me say a little bit about the development of particle physics over the last century or so. So many of the early discoveries in the first half of the 20th century were made not using particle accelerators, but using cosmic rays. So these were discovered in 1912 by Victor Hess. He went up into the atmosphere under a balloon, and he discovered that there was ionizing radiation coming down, created by particles striking the upper atmosphere. And when they come in, some of them are very energetic, and their energy is converted into showers of other particles, which ionize the air. So studies of these showers of particles revealed many different types of particles. For example, the first particle of antimatter was discovered in the cosmic rays. It was discovered in cosmic rays that there was a heavier brother or sister of the electron called the muon. And many other particles were discovered in cosmic rays also. But around the middle of the last century, it was realized that if you wanted to study these particles carefully, in detail, systematically, then what you would like is a source of energetic particles, a particle accelerator, and you would like to do experiments under controlled conditions. So that was what physicists started doing, as I said, around the middle of the last century. And, well, I don't know whether any of you still have an old-fashioned cathode ray TV in your homes. Anybody? No? Yes? Somebody? Okay, few. Okay, so you have got a particle accelerator at home, which works on exactly the same principle as the LHC. So you've got electric and magnetic fields which are used to accelerate particles and to bend their trajectories, and then you accelerate an electron beam. That electron beam hits the screen, and of course, then you use your eyes to detect the image. So we particle physicists have something a little bit more sophisticated than that TV screen. What we have is a detector, which is typically of cylindrical form, with various different layers that detect different types of particles that may be produced in our artificial collisions, much like those other particles are produced in cosmic ray collisions. So this is a cutaway view through one slice of one of the big detectors at the LHC. It's actually called CMS. It's one of the experiments at the LHC in which India is involved, and I'll come back to that a little bit later on. So over here, we have the point where particles collide, and then as they come out, they go through these various different layers of detector, each of which is optimized to look for a different type of particle. Maybe look for a photon, for example, or maybe look for some strongly interacting particle, or maybe a muon. I mentioned muons which go out through all the layers of the detector. So, particle physicists have been doing experiments of this type, of increasing sophistication over the last 60 or 70 years or so. And those experiments have given us what we call the standard model of particle physics. So this is a theory that was developed in the 1960s, in particular by Abdus Salam from Pakistan, whom you see here, and a couple of American theorists, Weinberg and Glashow. And they made essential use of some theoretical ideas proposed by Peter Higgs, to whom I'll come back in just a moment. Now, when they originally proposed these ideas, I think it's fair to say that many people didn't pay very much attention. But then, in the early 1970s, an experiment at CERN found the first experimental evidence for a new interaction phenomenon predicted by Glashow, Weinberg, and Salam, and so then people started to take notice. That first discovery was followed by many other measurements. In particular, at CERN in the 1990s, physicists from around the world did a bunch of really detailed and precise measurements of the standard model, verifying many of its predictions very accurately. So if you look over here, you see that little red dot there. Okay, that represents an experimental measurement. The green curve is the theoretical prediction. They agree perfectly well. And just a little note is that that red dot has been expanded in size by a factor of 10 so that you can actually see it. So this tells you how precise these measurements are. And this tells you that the standard model, we shouldn't really call it a model. It's a theory that we can calculate with great accuracy. Okay, so what does the standard model consist of? So obviously it contains the fundamental particles of matter. So some of these I've already mentioned. So there's the electron over there. There it's a heavier sibling, the muon, another even heavier one called the tau. Over here we have the quarks, so the fundamental constituents of nuclear matter. So we now know that there are 6 of them. And in between we have the neutrinos, neutral ghost-like particles that I'm not going to be saying very much about in the course of this lecture, although I will mention them briefly a bit later on. So those are the fundamental building blocks. But if you're going to build something, you don't just need blocks, you also need cement. You need something to hold those blocks together. And that's provided by 4 fundamental interactions. So one of them is gravity. And as I like to say, it keeps even the speculations of theoretical physicists firmly on the ground. Then we have electromagnetism. So electromagnetism was unified by James Clerk Maxwell just over 150 years ago, advertising spot while he was working as professor at King's College London. Then there's two other interactions that have short range and act within the world of elementary particles. So there's the strong nuclear force that holds quarks together inside protons and neutrons, and then also protons and neutrons inside nuclei. And there's a W particle, a heavy particle, which is responsible for the weak nuclear force. It's responsible for radioactivity, and if that force was not weak, then life would be impossible. Okay, so this is a roster of all the elementary particles known, at least up until 2012. And I like to think of these as being, in some sense, the cosmic DNA. Somehow these particles, their properties, encode all the information you need to make all the visible matter in the universe, even Donald Trump. Although how that happened, I don't know. Well, like Donald Trump, I just told you a lie. Because there is one thing that's missing. The issue is, where do those particle masses come from? So the electron has to have a mass. If the electron didn't have a mass, it would always travel at the speed of light, and it would run away from nuclei, and you'd never get any atoms. If this particle here, responsible for weak radioactivity, was not very heavy, then radioactivity would not be very weak, and we would all glow in the dark, and life would be impossible. So, an absolutely key ingredient in our understanding of the way the universe is put together is where particle masses come from. So, this is Mr. Higgs. I'm sure you've all heard the name Higgs, yes? Okay, good. So here he is, back in 1965, when he was working on his theory. So some of his secrets there, if you could read it. So he was the guy who provided the missing link in the Standard Model. He explained where particle masses come from. Now, you may say, well, just hang on a second. Didn't Newton tell us that weight was proportional to mass? You know, W is equal to mg. You all learned that in grade 9, I guess, don't you? And Einstein told us that energy is related to mass, E equals mc squared. But those two honorable gentlemen somehow forgot to explain where the mass comes from in the first place. They related lots of other things to mass, but they didn't give you a fundamental explanation of where it comes from. And so that's where Peter Higgs comes in, wearing a nice tie, and that's his theory on the blackboard behind him. Now, it's a key aspect of his theory that there should be a particle called after him, the Higgs boson, and this became, in the last part of the last century, in some sense, our particle physicists' holy grail, and that was the missing element of the Standard Model that was discovered at CERN in 2012. Now, I'm not going to attempt to explain that theory. Oh, another advertising spot. Yeah, he was a student at King's College London. Just saying. So I'm going to give you an analogy for how this Higgs idea works, okay? So you should regard empty space not as being really, really empty, but actually more like a medium. And then particles travel through this medium. And you can think of this as being analogous to trying to cross Siberia in the middle of winter. I'm not going to propose that you consider traveling through a snowfield. You know, here in Bangalore, I don't think you often get snowfields here, but you know about snow, and you know that in Siberia in winter they have a lot of snow, it covers everything, it's homogeneous, it's isotropic, it's a universal medium. And if you want to cross Siberia, well, you know, if you're lucky, you may have skis. If you have skis, then you skim across the top of the snow, you go very fast, you don't sink into the snow, and that's rather like a particle that does not interact with the Higgs universal field that fills all of space. As a particle that does not interact with the Higgs field travels at the speed of light, just in the same way that the skier goes extremely fast. Okay, but supposing that you're trying to go through this Higgs snowfield that fills the universe and you don't have skis. Supposing you have snowshoes. Well, if you have snowshoes, you're going to sink into the snow, you're going to interact with that Higgs snowfield, you're going to go slower than the skier, you're going to travel at less than the speed of light, like a particle with mass, an electron, maybe. And of course, you may be unlucky, you may not have any snow equipment at all, and you may be reduced to trying to walk through that Higgs snowfield in your boots, in which case you're going to interact very strongly with the Higgs snowfield. You're going to go very slowly, much less than the speed of light, much like a particle with a large mass. Okay, so that's the basic theory that Peter Higgs and others proposed back in 1964. Now, Peter Higgs pointed out that in such a theory, you have to ask yourself, what is the fundamental quantum of that Higgs snowfield? What is the fundamental constituent? So, in the case of the electromagnetic field, we know there's a fundamental particle called the photon. And he said, well, there's going to be a similar particle in the case of this Higgs field. In much the same way as there's a fundamental constituent of snow, which is the snowflake. So the LHC found that snowflake in 2012. It discovered the Higgs boson. Now you can pursue this analogy a little bit further because, of course, as you know, there's an almost infinite variety of different types of snowflake because a snowflake is a composite object put together out of water molecules, which can be arranged in different ways. And in the same way, people are still arguing, we were arguing this week, as to whether the Higgs boson might be just one of many, many particles made up of some sort of more fundamental constituent put together in different ways. So I got interested in the Higgs boson in 1975, and together with two colleagues, Mary Gaillard and Dimitri Nanopoulos, we wrote what was perhaps the first survey of what such a particle might look like. But in those days, these ideas were regarded as very speculative. And so rather cautiously at the end of our paper, we said, we do not want to encourage big experimental searches for the Higgs boson. Fortunately, our bad advice was ignored. Okay, so where are we with Gauguin's questions? So what are we? That, for a physicist, is what is matter made of, and as I've described, a key element of that is why do things weigh? What is the origin of mass? Is that due to a Higgs boson? Where do we come from? Well, that of course is the question, what is the origin of matter, that we'll be coming to later on. As I said, astronomers tell us that in addition to the visible matter, there's all that dark matter. That's also something that maybe we can answer with the Large Hadron Collider, the LHC. How did the universe evolve in the past? How is it going to evolve in the future? In order to answer that question, you need to know what particles there are in the universe, what interactions there are. Why is the universe so big and old? And of course, what is the future of the universe? So as I said at the beginning, our job as particle physicists is to at least ask those questions and provide whatever answers we can. I might mention, by the way, that when I was a PhD student, I had a copy of that painting by Gauguin on my office wall, just to remind me why I came into work every day. Anyway, the discovery of the Higgs boson at the LHC provided the answer to at least one of these questions. And now with the LHC, we're trying to look for some of the others. Okay, so let me relate this a little bit more closely to Gauguin's second questions, where do we come from? So this is just a snapshot of some of the key steps in the early history of the universe. So at the top here, we have the time about 300,000 years after the Big Bang when atoms were formed. Before then, the universe was so hot and so dense that you had nuclei, you had electrons, you had photons, but atoms could not bind. So, physics there was, but before then, there was no chemistry, no biology, no sociology, no Donald Trump. Now, if you go back when the universe was 3 minutes old, that's when nuclei were formed. Before then, there were no nuclei. There were the protons and the neutrons and the electrons and so on. But again, the universe was so hot and dense that those protons and neutrons could not stick together to form nuclei. If you go back before the universe was 1 microsecond old, there weren't even protons and neutrons. There would have been lots of quarks running around the universe, but again, they couldn't have stuck together. And if you go back to when the universe was 1 picosecond old, so a millionth of a second old, that's the time when we think the Higgs started doing its stuff and you started having particle masses. If you like, one way of thinking about it is that before then, the universe was too hot for that snowfield to settle on the ground throughout the universe. So what we think is that the dark matter may have appeared sometime between 1 microsecond and 1 picosecond after the Big Bang, and matter itself may have appeared sometime around 1 picosecond after the Big Bang, or perhaps earlier. And those are two of the key questions that we're now addressing with the CERN LHC. Okay, so here is a picture of the layout of the Large Hadron Collider. So large, yes, large, 27 kilometers circumference. Collider, collider. Hadron, hadron, that's just the name that we use for the particles that circulate inside the ring. So you can judge how big it is by reference to the Geneva Airport runway over here, okay? So you don't actually see the collider itself from the air because the collider is in a tunnel which is on average about 100 meters underground. So if you go inside that tunnel, what you see is a ring of tubes, and inside those tubes there are magnets which bend the particles around, just like in the old-fashioned TV sets, and they keep them going around in a circle so that then they can go around many, many times and collide with each other. So when it's in full operation, you've got thousands of billions of protons. Each of them has approximately the energy of a fly. They travel very close to the speed of light, and they make maybe 1 billion collisions per second. And in those collisions, we hope to find the origin of mass, maybe find dark matter, maybe understand the difference between matter and antimatter, and generally to understand the primordial plasma that filled the very early universe when it was just a fraction of a second old. So the LHC has been running for several years now. It started in earnest in 2010, and now we're in a second run of the accelerator, making collisions at higher energies. This TeV thing, this is a unit of mass energy we particle physicists use. A TeV is, roughly speaking, 1,000 times the mass energy of a proton. So you can imagine that what we do is we're colliding protons. Each of them has almost 10,000 their rest mass energy. That takes us back to something like 3 times earlier in the history of the universe than we were able to do with the first run. Okay, so now let's look inside one of those tubes. And this is what you see. So you see a bunch of smaller tubes. And 2 of these are where the particles go around, so the particles going around in opposite directions so that they can collide. Of course, in order for them to collide, you want to be sure that the particles, the protons, don't get stopped by collisions with gas in those tubes. And so those tubes are actually vacuum pipes, and the vacuum in those pipes is better than on the surface of the moon, all around those 27 kilometers. Now, just to annoy the cosmologists in the audience, I would also argue that the LHC is cooler than cosmology. So this is a picture of part of the LHC refrigeration system. And what it does is it cools the magnets down to 1.9 degrees above absolute zero. You want a very cool magnet because then you can get a very strong magnetic field, and that way you can bend particles around even if they have extremely high energies. So these magnets are a lot more powerful than what you have in your TV set. For comparison, the universe, as I mentioned earlier on, is full of radiation emitted just after the Big Bang, 300,000 years after the Big Bang. And that radiation nowadays has an effective temperature of 2.7 degrees above absolute zero. So that's why I argue that particle physics is 0.8 degrees cooler than cosmology. Okay, so you've got these particles going around in these magnet rings, and as you go around, there are 4 points where the particles collide. So this is a cutaway drawing illustrating the layout. So 1, 2, 3, 4 places where we make collisions. And I would like to highlight in particular this location here called CMS, and that location there, Alice, because that's the location of the 2 experiments that India is involved with. So I showed you earlier on a simplified cutaway drawing of what a particle detector looks like. These are some images of the real thing during the period of construction. So here we have CMS. This is part of the muon detection system of CMS, and the particles collide in the middle there. And CMS was one of the 2 big detectors that set out to look for the Higgs boson and is now looking for dark matter. So then there is its friendly competitor, ATLAS, which you see here. So these tubes here, these are part of the magnet system of that detector. Now, if you look very carefully, you will see a person. Okay? I promise you, that's a full-size person. It's not a Lego person. It's a real person. And that tells you how big this detector is. It's something like 25 meters tall and almost 50 meters long. So that was also looking for the Higgs boson, is now looking for dark matter. The Alice detector over here, that's studying this primordial plasma that filled the universe when it was a fraction of a second old. And this one down here, LHCb, this is one that is trying to understand the very small differences that have been observed between matter and antimatter particles that may be connected with the origin of the matter in the universe itself. So as I mentioned, India is involved in 2 of these experiments, specifically in CMS and Alice. So Indian physicists were part of the team that discovered the Higgs boson 5 years ago, and they're part of the team that's now looking for dark matter. I should perhaps have mentioned, by the way, that these experiments take place at CERN, but they're not just done by CERN. They're actually done by collaborations of literally thousands of people from around the world. So this is a map showing all the countries around the world from where those physicists come. So dozens of countries, hundreds of institutes. So the blue countries are the member states of CERN, the host laboratory. The paler blue countries, including India, are associate members of CERN, so sort of half members of CERN. And India just became an associate member recently, and you can see there's a few other countries as well. Okay, so what were all these thousands of physicists looking for? So they're looking for something like this. So this is a computer simulation which shows you what might happen if you collide a proton coming from this direction and a proton coming from that direction. So they have a large amount of energy. That energy can be converted into particles, dozens, maybe even hundreds of particles. Some of them are charged and they leave tracks in the detector, those yellow lines there. Some of them are neutral, so they don't leave tracks, but they deposit their energy in some outer part of the detector, which is represented by these blobs here. Now, what you see in this picture is that two of those blobs are much bigger than the other ones, those two blobs over there. So that is where two very energetic particles, probably electrons, came out of the collision. And those electrons might have come from the decay of a Higgs boson. See, the Higgs boson is an unstable particle. It decays very quickly. You can't see it directly. The best that you can hope for is to see what it disintegrates into. And in this simulation, it decayed into those two energetic electrons over there and two energetic muons over there. So that's an example of the sort of thing that the experiments were looking for. So, now let me talk a little bit about the discovery of the Higgs boson, which I think it's fair to say generated mass Higgsteria in the particle physics community back in 2012. So that discovery was based on the observation by ATLAS and CMS of interesting events characteristic of a Higgs. So I showed you previously a computer simulation. This is a computer reconstruction of a real event in the ATLAS detector. So again, you can see these yellow lines representing charged particles. And here you can see 1, 2, 3, 4 very straight red lines. Those correspond to very energetic particles, probably muons, that might have come from the decay of a Higgs boson. And this is an event observed by the CMS experiment. So in this case, there's no charged particle line, but you do see here this large deposit of energy. And that could very well be a photon. So there's two energetic photons in this event. And that's one of the signature possibilities for the decay of a Higgs boson. In fact, it's something that we calculated in that paper we wrote back in 1975. Now, if you just see one or two events of that type, you can't be sure of the interpretation, because sometimes other processes within the standard model could mimic what a Higgs boson looks like. But if you see enough events of that type, if you see a big statistical excess of such events, then you can be sure that there's some new physics going on that might be the Higgs boson. So that's what happened on July the 4th, 2012. So what was announced then by ATLAS and CMS was the discovery of a new particle. And as you can see, this news was well covered in Indian newspapers. So this is a view of the main CERN auditorium that day, a whole bunch of happy physicists. And in the front row, we got a bunch of happy and possibly slightly relieved directors general of CERN. So this guy, Chris Whelan-Smith, was the person who persuaded European governments to pay for all this. This is Lynn Evans, the guy who actually built the accelerator. And these are some of the other CERN directors general. So this picture I like for two reasons. So one reason is that here you see Peter Higgs, and here you see one of the other theorists who proposed these ideas back in 1964, called François Englert. So they proposed their ideas back in 1964, and then they had to wait for 48 years. And amazingly, they never met in all that time. This is the instant when François and Peter Higgs met. Of course, the following year, they met again in Stockholm. Peter Higgs, by the way, said that he had never expected to live to see his particle discovered. So that's one reason why I like the picture. The other reason why I like this picture is because this is Fabiola Gianotti, who was the person who presented the ATLAS results that day and is now the CERN Director General. So, what did the experiment see? Nothing. So what I show here is, as a function of the possible Higgs mass, the data with standard model processes subtracted. Some fluctuations here and there, but nothing significant. So you don't see any Higgs here. But if I take away that white band, then you see a highly significant statistical excess. There's no doubt there's a new particle. But that's not the end of the story. You discovered a new particle while you were looking for the Higgs boson, but it might be an imposter. It might be something completely different. And so the key question was, is this really the Higgs boson finally emerging from the standard model background? So over the last few years, there have been a lot of continuing follow-up studies of the Higgs boson, which we also discussed in the course of our meeting this week. So I compare the situation to if you've been doing a jigsaw puzzle for 100 years with dozens of pieces, and eventually you find a piece in the back of the sofa that looks like it might be the missing piece, but of course you have to check whether that missing piece has the right shape and the right size to fit into that gap in the puzzle. So this is one analysis that I did with my student Tivong Yu. So the Higgs is supposed to give masses to other particles. That means that it should couple, connect, interact with other particles proportional to their mass. So that's something that we checked. So the standard model says that the data should lie along that red line, and as you can see, the data do lie along that red line. So we wrote in our paper that this particle walks and quacks like a Higgs boson. Peter Higgs could smile. And subsequently, this analysis has been done much better by ATLAS and CMS. And as you can see here, again, the data look exactly like the prediction of the theory. So this discovery was certainly a big deal. Without the Higgs, there'd be no atoms because electrons would run around at the speed of light and they would escape from nuclei, they'd never bind. There'd be no heavy nuclei, in fact. Weak interactions would not be weak. As I've already mentioned, we would glow in the dark, life would be impossible. So the existence, the discovery of the Higgs boson was indeed a big deal. So it's not altogether surprising that in 2013, Peter Higgs and François Englert got the phone call from Stockholm, and the Nobel Prize Committee announced that beyond any reasonable doubt, this particle is a Higgs boson. What I didn't know is that when we submitted our paper to the journal, the referee of the paper said that beyond any reasonable doubt is not a scientific judgment. And the referee forced us to take that quotation out of our paper. So it doesn't appear in the published version. Not good enough for the journal, but good enough for the Nobel Prize Committee. Okay, so now I will slightly paraphrase James Bond by claiming that the standard model that I've been describing up to now is not enough. And in deference to James Bond, I give you 007 reasons for saying that. The first is that, according to the standard model, empty space is unstable. Come back to that in a moment. The standard model does not explain the dark matter. The standard model does not explain the origin of matter in the universe. It doesn't explain why particles have the masses they do. It says that they can have a mass, but it doesn't tell you how big. Doesn't tell you about neutrinos. It doesn't tell you why the universe is so big and old. It doesn't make a quantum theory of gravity. That's why those guys in the front row still have jobs. So, lots of things for people to work on, including all you students out there. So many of these problems are being studied with the LHC, and I'll now want to just go through some of them in the remaining time. So, the instability of the vacuum. So, in the standard model, the stability or otherwise of empty space depends on the mass of the Higgs boson on the one hand and the mass of the heaviest quark, the so-called top quark, on the other hand. And if you're in this region of space over here, then our vacuum is stable. If you're up there, it's unstable, according to the standard model. The data from the LHC seem to tell us that we're in this region up here, in this unstable region. So what does this actually mean? Well, I think it means that we need some sort of new physics, because I don't believe that the universe is going to collapse tomorrow. But theoretically, it could. So to avoid that, let's postulate some new physics. So here's an illustration of the problem. So we're over here. We've got a Higgs snowfield. The snow has a certain depth, okay? But over there on the right-hand side, there's another region of the theory where the density of that Higgs field is much, much deeper. It's as if everywhere was covered with some enormously thick snowdrift, and the properties of all the particles of the entire universe would be completely different. So you're saying, okay, fine, there's some place over there that we don't want to be, but we're not there, we're over here. Well, not so fast, because according to quantum physics, the Higgs snowfield is going to be fluctuating all the time, and there is some possibility that it will actually go through over into that region of very dense snowdrift Higgs field. Well, if you calculate the probability of that happening today, it's very small, much less than the possibility that Donald Trump would start a nuclear war. It's not quite a joke. However, back in the very early universe, those fluctuations would have been much, much larger. And it's very difficult to understand why the entire universe wouldn't have gone over into that big crunch snowdrift, unless there is some barrier that stops that from happening. And so I think that we should be looking at theories that do prevent that from happening. And one of them is my own personal favorite, called supersymmetry, that I'll be discussing in a moment. So that was my first reason for saying that we should have physics beyond the standard model in order that the vacuum be stable. The second one that I mentioned was dark matter. So here's a guy, Fritz Zwicky, who back in the 1930s, looking at the motions of galaxies in the Coma cluster, found that they were moving too fast. That in order to hold them together inside that cluster, you needed a stronger gravitational field than was produced by the visible stuff. So he said there has to be a whole bunch of invisible dark matter there that increases the gravitational field so as to hold those galaxies together. And that's the dark matter. It's some sort of invisible, heavy stuff. In the 1970s, the case for dark matter was greatly strengthened by Vera Rubin, an astronomer whom you see here, who looked at the motions of stars in galaxies, and she also found that they were moving too fast. That unless there was an additional gravitational field generated by additional dark matter, you couldn't understand how the stars were held together inside the galaxies. So, a second very strong motivation for dark matter. So this is a little picture that illustrates the problem. So here you have the velocities of planets as they go around the sun. And you know Kepler's laws, the velocities should decrease as you go further from the sun, and they do. And that's because the mass of the solar system is largely concentrated in that nuclear reactor sitting in the middle. But if you plot the velocities of the stars in their orbits in a typical galaxy, you find that they don't go down as a function of distance, they just continue forever. And that tells you that in addition to the visible matter, there has to be some large cloud of invisible dark matter which stretches out and generates additional gravitational field to hold those stars in place. So, here we are, typical galaxy. This could be our star, just there. According to this theory, we are swimming in a sea of dark matter. So what is that dark matter made of? So there's many different theories about that, and we've been discussing a lot of them in the course of our meeting this week. But one of the possibilities is that it's some sort of heavy, invisible particle, and my own personal favorite for that is something called supersymmetric particle. So according to this theory, in parallel to all the known particles, represented by these little spheres up there, there are partner particles, supersymmetric partner particles, which are generally much heavier. Most of those heavier particles are unstable, they decay, but the lightest of those supersymmetric particles would be stable and would have just the right characteristics to be the dark matter that is wanted by those astronomers and cosmologists. So over on the left here, I've got all the particles that we know and love, and over on the right here, I've got all their supersymmetric partners that we would dearly like to know, and we would love to love them if we could actually discover them. But no evidence so far. So how could we hope to observe these new particles? So here I have a representation of the possible interactions between dark matter particles and standard visible particles. So back in the very early universe, there would have been a lot of dark matter particles. Most of them would have annihilated, and when they annihilated, they would have produced standard model particles. So what we do at the LHC is we reverse the process. We collide standard model particles, protons, and then we hope that we will produce pairs of dark matter particles. Now, we at CERN, we at the LHC, are not the only people looking for dark matter particles. There are also people who look directly for dark matter. So they look in this direction in collisions of dark matter particles with standard model particles, which could be observed in suitable underground laboratories. So just to give you an idea, if you have a bottle of water, then there's a chance of maybe 1 in 10 that at any given instant there's a dark matter particle in there. Unfortunately, that dark matter particle would interact very weakly, and it's going to be traveling at something like 1,000th of the velocity of light, so it's very difficult to detect it, but in principle, with a suitable detector, you can do it. So those are two of the ways of looking for dark matter, producing them in particle colliders, or looking directly for astrophysical dark matter. You can also hope to look for dark matter particles that are annihilating today in outer space, although I won't mention that any further. So this is what you do at the LHC looking for dark matter. You look for events where you can't see the dark matter directly, but those dark matter particles carry away energy and momentum. So what you look for events is where there's a sort of imbalance, where you see lots of energy coming out on one side of the detector, but nothing on the other side. And that nothing on the other side isn't really nothing, it's nothing visible, but it could be invisible dark matter particles. So ATLAS and CMS have been looking for such events, but so far without any luck. So no sign of dark matter, no sign of supersymmetry. It must be said also nothing else new beyond the LHC has been seen either, but of course we're continuing the search. So how else would you look for dark matter apart from the LHC? Well, as I mentioned, you could look for dark matter scattering off regular matter. So to do that, typically you go to some deep underground laboratory with very low background from cosmic rays and from radioactivity, and you look for very rare events where some dark matter particle comes through and hits a nucleus and kicks it off in a recoil. So one of the things that we've been discussing at our meeting this week is comparison between these direct searches for astrophysical dark matter and the searches for dark matter production in collisions at the LHC. And I think it's fair to say that these two ways of looking for dark matter are largely complementary. And I think these efforts will continue in the coming years, and the sensitivity of both the LHC and these dark matter searches will increase significantly. So fingers crossed, maybe we're going to discover dark matter. So, Star Trek. I think Star Trek is largely responsible for the fact that whenever CERN issues a press release about antimatter, the media are very interested. They could also be interested because of angels and demons. But I can assure you that CERN does not make enough antimatter to blow up the Vatican or indeed to power up the Starship Enterprise. What we're interested in is how and why do matter and antimatter particles differ. So antimatter was postulated in the 1920s by Paul Dirac, whom you see here together with anti-Dirac. And so he said, well, there should be these antiparticles with the same masses as regular particles, but opposite electric charges, opposite internal properties. And in fact, this sounds like a very abstruse theoretical idea, but in fact, a few years later, the first antiparticles were discovered in the cosmic rays, and nowadays they're used routinely in medical diagnosis. Thousands of people each year have what's going on inside their bodies analyzed using PET scanners, where the P stands for positrons, your antiparticles of electrons. Now, it came as a big discovery about 50 years ago when experiments discovered that actually positrons are not antiparticles are not exactly equal and opposite to particles. So we have a model that describes that within the standard theory, but we don't really have an explanation. And it's been suggested that maybe this very small difference between matter and antimatter might be connected to the fact that in the universe as a whole, we see large clumps of matter in the form of stars, planets, and so on, but we don't see large clumps of antimatter. And experiments at the LHC and elsewhere are trying to understand this difference between matter and antimatter and maybe make a connection with this cosmological dominance of matter. So this connection was proposed by the Russian physicist Sakharov in 1967. So he is a little bit later visiting CERN to try to understand what experiments we were doing. And he pointed out that if you have this small difference between matter and antimatter, and if you have interactions that are capable of creating matter, which have been predicted by theories, although not yet seen by experiment, and if you have a suitable glitch in the expansion of the universe, then those differences between matter and antimatter interactions could build up an excess of matter over antimatter, and that excess of matter could be what we're made of. So that's a very enticing idea, and there's a dedicated experiment at CERN and also experiments elsewhere looking into this possibility. Finally, I would like to return to our friend Albert Einstein. So here he is, a little bit older than in the first picture, and maybe a little bit sadder, possibly. Maybe because he had a premonition that he was not going to succeed in making a unified theory. So this is his final blackboard, which I'm sorry to say does not have a unified theory. On the other hand, many of the ideas that Einstein worked on, people are still working on, including those gentlemen in the front row. And one of the ideas that he worked on, that people are continuing to work on, is the possibility that there might be additional dimensions of space. Now, in some of those theories with additional dimensions of space, gravity can become a strong force at the energies of the LHC. And in some of those theories, when you collide protons, it's possible that you might make a microscopic black hole. So when the LHC started, some people got a little bit nervous that maybe we would make black holes that could eat up the entire Earth. So, of course, this is garbage. If we could make dangerous black holes, then cosmic rays would have been making them for billions of years, but we're still here. So no need to worry. And in fact, theoretically, if they existed at all, these things would vanish instantly. But there was one good thing about this black hole saga. It meant that when the LHC was switched on, maybe 1 billion people could watch on the TV. And I think they were watching not because of the Higgs boson, but because of the possible black holes. Anyway, so far, no black holes either, but we're still looking for them. So this is a graphic that was produced by The Economist, showing the time lag between the proposal of new particle and its experimental discovery. So in the case of the Higgs boson, that was 1964 to 2012, 48 years, which gave time for Peter Higgs to evolve from that to that. And so I tell my supersymmetric friends, be patient. All lovers of physics beyond the standard model know it took 48 years for Peter Higgs, maybe just a few more years. So hang in there. So anyway, that brings me to the end of what I wanted to say. Universe is like an iceberg. So there's a small amount of visible matter, but hidden there is the dark side of the universe. And the standard model explains perfectly well the visible matter, but I am sure will soon be sunk by the dark side. Thank you very much.
Thank you very much, John. That was really enthralling, I'm sure, for many of you. And I guess you have questions. If you do, please put up your hand. Please wait for the mic. Please say where you're from. And there's the first question there. And please keep your questions short, precise, hopefully, and to the point of the lecture.
Yes. Hello, I'm Kaustav Mitra. I'm from Presidency University, Calcutta. So my question is that can you explain in a very simplified way that what is the fundamental difference between the interactions for which mass needed another Higgs boson to be explained its origin, whereas the other charges of other fundamental interaction, like the electronic charge or colors, like things like that, they didn't need such bosons to be explained their origin?
Okay, well that's a very good question. It is actually quite possible, and there's a lot of discussion about it, that actually there is a field associated with the other charges, like the electric charge. It wouldn't be the photon. The photon couples to the electric charge, but it wouldn't be responsible for the existence of electric charge. But it's possible that some other field, as for example in string theory, could be responsible for that charge. But if so, my guess is it's probably beyond the reach of our current experiments.
Good evening, Professor. My name is Akshita from RV College of Engineering, Bangalore. So my question is regarding the quantum computers D-Wave, which is a joint association of Google and NASA. So supposing in the next decade we are successful in in designing and building a quantum computer, what are the questions that we are going to ask the quantum computers? And in other words, what are those questions which the computers now do not solve?
Well, this is not really my field. Of course, in our business of particle physics, we are continually in the business of trying to get more computing power. In fact, I remember when the LHC was being discussed, the head of the CERN IT department making a presentation saying that in order to analyze LHC data, we would need 1,000 times more computing power than what we have at the moment. But he said, that won't be a problem. And it wasn't a problem. Okay. So I honestly don't know whether quantum computers will play a role at the LHC in the future. But I'm pretty sure that if there are a lot of quantum computers about, a lot of banks are going to have to change their encryption systems.
I don't know if many of the audience know, but the World Wide Web has its origin in CERN in some deep way, right?
Well, yeah, the World Wide Web was invented at CERN in order to enable those thousands of physicists from those hundreds of institutes to collaborate together. And that was done in about 1990. And then in order to analyze the data from the LHC, we, with our collaborating institutions, went one step further by linking together computers all the way around the world so as to analyze the LHC data much more effectively. I can tell you a computing joke afterwards, but maybe not in public.
Hello, sir. My name is Mahesh. I'm from St. Joseph's here. I have this question for a while. Like you told about the Big Bang, right? The dimension of the universe, it's 10 power, like as of now, the width is 10 power 28 centimeter and the length is 13.6 billion light years. Like the difference is very drastic. So like, what can you tell about the bang besides the fact that it was asymmetrical, and is there any data that you can extract from what we know?
Okay, so thank you for that question. So, as I mentioned, the earliest piece of information that we can extract from the universe so far is this radiation that was emitted something like 300,000 years after the Big Bang. Now, if you remember the image of that, it has sort of funny little speckles of different colors. And we believe that those are due to processes that occurred just after the Big Bang. People argue about how long after, but maybe 10 to the minus 35 seconds after the Big Bang. Okay. Now, so there's a whole range of experiments now which are trying to understand those features and to see whether they can relate them to some properties of physics that we can measure with our colliders. And that's also one of the things that we've been discussing here this week. But in general, I think that we physicists should be a little bit modest. I mean, okay, we can think about what happened a millionth of a second after the Big Bang, or maybe 10 to the minus 35 seconds after the Big Bang. But t equal to 0, I think we should stay away from. Because our ideas about space and time and gravity break down at that stage. Of course, some of my colleagues speculate about it, but I prefer to stick to time bigger than 0, and I'm not even sure whether time equal to 0 ever actually existed.
Good evening, sir. My name is Santosh. I belong to IISc, Indian Institute of Science, Bangalore. I have a question. You mentioned that you use these LHCs and they accelerate particles to very high energies. Do you think this LHC would continue to be in use? Now that we have laser plasma wake field accelerators, do you think there would be a replacement for LHCs?
Okay, thank you for that question. So, as I mentioned, just recently we've increased the energy of the LHC, but we're still ramping up the number of collisions that we make. And we plan to run the LHC for at least another 15, maybe 20 years, making more and more collisions. We aim at getting 100 times more collisions than what we've got so far. And that's hopefully we're going to reveal to us the secrets of dark matter or some of Gauguin's the answers to some of Gauguin's other questions. So what's going to come after the LHC? This is your question. So it could be that we'll just continue with the same type of accelerator technology that we've been using up to now. And in fact, both in Europe and also in China, ideas are being discussed for making a bigger tunnel and putting in more powerful magnets, which would enable us to increase the energies of collisions by maybe a factor of 7. Now, there are ideas for novel accelerating technologies, like you mentioned, like plasma wake field acceleration. And we do have an experimental setup at CERN that's pursuing that sort of studies. I think it's going to be very difficult to actually build a high energy accelerator using that technology, at least for quite some time to come. Because if you want to build a high energy accelerator, your beams must be very well concentrated. Because if they're just spread out all over the place, you don't get very many collisions. And you have to be very efficient in the way that you transfer energy from the plug in the wall into the beam. And these, I think, are two of the issues that have to be solved. And that, I think, is going to take some time.
Thank you.
Hello, excuse me.
Good evening, sir. I'm basically a physics teacher from a college. By name Vijaya College. I am retired actually. I just want to ask you a question. Actually, in CERN, they are conducting the experiment 100 meters below the ground. Is there any specific reason to do the experiment below the ground at a depth of 100 meters?
Okay.
And further, why is there any necessity to cool the experimental setup to minus 271 degrees Celsius is what I want to ask.
Yeah. So the reason for having underground is basically a practical issue. So the first CERN accelerators and other accelerators around the world were built on the surface. So for example, in the US, they built an accelerator which has a circumference of 6 or 7 kilometers entirely on the surface. That's because they were doing it in the Great Plains in the United States where it's very flat, okay? So in the neighborhood of Geneva, it's not very flat, okay? There's hills, there's a lake, there's mountains, and if we wanted to build an accelerator, we had to go and dig a flat tunnel underground. And so this CERN did already in the 1970s, and that was the only way in which we could dig the tunnel to prepare a space for the LHC. So I mentioned the fact that we're currently discussing the idea of building an even larger accelerator, and so as you can probably guess, that's going to be in an even deeper tunnel, which is actually going to have to go under the lake of Geneva. Now, as for the temperature, so we cool the magnets down to that very low temperature because that's when we can get the strongest magnetic field. And we need that strong magnetic field in order to bend the particles to go around in circles. Remember, we're aiming for particles which have very high energies, and the bending power of a magnet is proportional to its field. But once you're outside the magnet, if you go down in the LHC tunnel outside the magnet, then the temperature is about 17 degrees year-round.
Hello, sir. I'm Srivatsa from PS University. My question is, can you trap Higgs Boson so that you can study its behavior?
No. If you have an idea for doing it, just let me know.
Sure.
So your first problem is that the Higgs boson is an unstable particle. It decays in something like 10 to the minus 20, 10 to the minus 21 seconds. So, okay, it's unstable. And the second problem is that it's a neutral particle, so you can't build a sort of trap using electromagnetic fields. So we routinely build traps for particles, including traps for antimatter particles, including traps for anti-atoms, but not for the Higgs boson.
Good evening. My name is Sachin Bharadwaj. I'm from RV College of Engineering, a research fellow at JNCASR. My question is about two things. The viability of the proposal that detecting dark matter is one of the most toughest jobs right now, because we don't get information from dark matter. So would it be wise, instead of searching for dark matter, to search for the supersymmetric or the reflected anti-dark matter, which could give out information instead of the dark matter which won't give out information? That's one. The second thing is, would perturbations of dark matter produce some kind of information signals that could be detected?
Okay. So what we actually do at the LHC is we don't actually look directly for the dark matter particles because we can't see them. But what we expect is that if a dark matter particle is produced at the LHC, that's through the production of some heavier supersymmetric particle that then decays into the dark matter particle. And so these experiments that are looking for missing energy look for missing energy in association with all that other stuff coming from the heavier supersymmetric particles. Now, I think a sort of, perhaps the more sort of basic aspect of your question is, what is the guarantee that you're actually going to discover dark matter? And I think there is no guarantee. We do the best that we can, but it may be that dark matter takes a different form from what I described. And there are other experiments looking for different types of dark matter in various different ways. But my own personal belief is that dark matter is in some sense the most pressing experimental problem that we have to resolve. Right? The astronomers, the astrophysicists, the cosmologists tell us that this dark matter really has to be there. And that is, I think, the most solid piece of evidence, experimental evidence, that we need some physics beyond the standard model. And it's something that I think we have a decent chance of addressing with our ongoing experiments.
Maybe
Excuse me.
There was a component about perhaps at a astrophysical level where the perturbations of the dark matter...
Right. Sorry. Yeah, so of course, astronomers do quite detailed observations of the distribution of dark matter, which they can infer, for example, from its effect on gravity, the effect of gravitational lensing. And for example, another one of the topics that we were discussing this week was when I was talking about these flat rotation curves. Are they really strictly flat and featureless, or are there some sort of bumps in them? And those bumps might be characteristic signatures of particular types of dark matter particle. So I think that people are thinking along the lines that you suggest.
Excuse me, sir. Can I ask? Yeah. Sir, in your presentation, you had given that after the Big Bang, like in a picosecond, quarks were formed, and after like 3 minutes, you had the formation of protons and neutrons. Like, how do you know that time duration? Like, how long did it take for protons and neutrons?
Okay, so we can see the way in which the universe is expanding today, and then we can, if you like, run the clock backwards in our minds and calculate what would have been the effective density of stuff, the effective temperature of the universe at various different time stages in its early expansion history. Now, just to clarify maybe what are the various different time stages. So about 380,000 years after the Big Bang, the universe cooled sufficiently for atoms to form. So before that, you had the plasma. That plasma was made up of nuclei and electrons. The nuclei were formed when the universe was about 3 minutes old. And the protons and neutrons, they were formed when the universe was about 10 to the minus 5, 10 to the minus 6 seconds old. So that gives you some idea of the time scale. Those, I think, are fairly well understood in terms of the fundamental features of cosmology and the fundamental properties of particle interactions.
Sir, and what do we know, like, everything starts from the Big Bang. What do we know before the Big Bang? What was there before?
So that's a question that I always refuse to answer. So what some of my esteemed theoretical colleagues speculate about what happened before the Big Bang. But as I said in answer to one of the previous questions, I don't even allow myself to think about time equal to zero, because I think that our understanding of physics breaks down before we reach that point. And so a fortiori, I don't think about what happened at time less than zero. I'm not even sure that time less than zero actually existed.
Thank you.
Good evening, sir. Sir, here.
Oh.
Sir, I am Srishti Chauhan from Mount Carmel College. I have a question like the supersymmetric particles. Can there be a supersymmetric energy also? Like a supersymmetric energy to the light, which can be much, much faster than light in the darker side of the universe?
So there is a supersymmetric partner of the particle of light. So the particle of light is the photon. There's the photino, which is its supersymmetric partner. But it has a mass. And that means that it always travels at less than the speed of light. And the speed of light is a really universal speed limit. Nothing can travel faster than the speed of light. And the only way you can travel at the speed of light is if you have no mass, even if you're supersymmetric.
Good evening, sir.
Go ahead.
Yeah. Good evening, sir. I think you mentioned that there are specific fields associated with other properties of matter such as charge, which you said may not be accessible to our current experiments. So how do we propose to go about studying those? And secondly, you mentioned that the Higgs boson itself might be composed of certain subparticles. So when is that going to end? Like, when is the ladder going to end?
Okay. So I think I cannot avoid talking about string theory any longer. So many of us think that the underlying quote-unquote theory of everything is something related to string theory. So string theory started off as the idea that what we think of as being point-like elementary particles are actually extended objects, extended in one dimension, like pieces of string, maybe pieces of string with ends, or maybe closed loops of string. So then later on, in particular in the 1990s, people realized that things were more complicated than that, and that there would also be objects that were extended in more than just one dimension, like membranes. And so now we talk about brain theory, which is some sort of complicated mishmash of all these things. Now, within the framework of string theory, correct me if I'm wrong, but we believe that charge is related to one of the specific fields associated with string theory. And that's what I had in mind when I said that we believe that there is some field that is associated with electric charge in the same way that the Higgs field is associated with the value of mass. However, whereas the mass of the Higgs boson is low enough that it's accessible to our current accelerators, it's about 130 times the proton mass, the quantum associated with the field that might be associated with charges in general would potentially be many, 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 many orders of magnitude larger.
Hello sir, I'm Poulomi from Indian Institute of Science. I want to ask that the graph of the data you showed when Higgs boson was detected, in x-axis mass was plotted in giga electron volts. What was plotted in the y-axis and how does it let you know that Higgs boson is detected?
Okay, so I actually showed two pictures of that type. Let's see whether I can find them. So I showed this one. So this one, as you say, there's a mass on the horizontal axis, and on the vertical axis, it's the number of events that were seen with subtracted the number of events from other standard model processes. So producing quarks, producing W particles, producing, you name it, okay? So that stuff you calculate in the standard model, you subtract that from the data, and you see what you're left with. And of course, there's going to be fluctuations, right? And so you see these statistical fluctuations here. But then, as I commented, if you look in this specific mass range over here, which is around 125 GeV, corresponding to about 130 times the proton mass, there's a clear excess. Okay. And then, of course, the issue is, what is that excess? It's certainly a new particle, but is it the Higgs boson? So the second graph I showed was this one. And on this one, again, I have the mass, but this time it's the mass of other particles, like the W boson or the Z boson or the top quark or the bottom quark. And the vertical axis here, this is the strength with which they interact with, couple to the Higgs boson. So in the standard model, that coupling should be proportional to the mass, that's the red line, and the dashed line, that's our fit to the data, which agrees very well. So the first plot showed you there is a new particle, and the second plot tells you it's very much like the Higgs boson. And sorry, I realized that I only answered a half of the previous question. So there still is a lot of discussion going on about whether the Higgs boson is composite, made up out of little things rattling around inside. And this we're trying to examine experimentally by measuring these coupling properties more and more accurately, and also to look whether there are additional couplings, additional interactions that are not described by the standard model. And that's again something which we've been discussing a lot this week.
So so I think we have to cut off right now. I'm sorry, but you can ask John over tea. So let's thank John again for a splendid lecture.